Imagine the roar of a jet engine versus the absolute haunting stillness of a midnight forest. A hawk's hunt is announced. Wing beats, wind, panic. An owl? No warning at all. 1 second the night is whole, the next a vole is gone, and nothing in between makes a sound. This isn't magic. It's a biological engineering wonder. Tonight we'll deconstruct the tiny serrations, the velvet down, the facial disc, and the wing geometry that let these birds annihilate what we call air noise. We'll show you how an owl breaks the rules of fluid dynamics and how engineers in 2026 are copying it to make drones whisper through the sky. By the end of this video, you'll understand how an owl triangulates sound in pitch-black woods, how it aligns its strike down to the decibel, and why its silence could change everything, from delivery drones to wind turbines. But first, have you ever heard an owl approach? Write yes or no in the comments right now. Hey everyone, welcome back to Wild Spaces. If you love deep dives into animal superpowers and how nature inspires technology, hit subscribe. Today we're doing a detailed step-by-step breakdown of Acoustic Camouflage, the suite of adaptations that render owls effectively invisible to sound. First, we'll examine the feather microstructures, those comb-like serrations and velvet surfaces. Then we'll look at the owl's sensory setup, facial disc, asymmetrical ears, binaural hearing. After that, we'll analyze the flight mechanics, wing shape, glide angles, and how owls bypass turbulent sound. Finally, we'll jump to modern engineering, drones, turbines, and stealth tech inspired by owls. Questions along the way, I'll ask you to answer in the comments so we can discuss. Let's go. Start at the edge of the wing. Owl flight silence starts with microgeometry. The leading edge of many owl species has long, comb-like feathers called fimbriae, tiny serrations that break up the wing's contact with air. Think of them as a sound diffuser. Next, velvet-like down on the top surface of wings. That fuzzy layer absorbs and stabilizes the turbulent microeddies that normally create broadband noise. Instead of a single loud whoosh, you get millions of tiny chaotic movements that cancel and dampen each other. Finally, the trailing edge is soft and fringed, so the air peels off smoothly instead of snapping and shedding vortices. The combined effect, low amplitude, broadband pronounced sound, is replaced by whisper-level turbulence, often below the hearing threshold of their prey. Which feather feature surprised you most? The serrations, the velvet, or the fringed trailing edge? Tell me below, and I'll pin some replies. Owls don't just hide sound, they exploit it. Their facial disc is a parabolic reflector that funnels sound toward the ears. The shape is adjustable. Feathers reconfigure the disc like you move a satellite dish. Many species have asymmetrical ear openings, one higher than the other. That vertical offset gives them elevation cues for incoming sound. Combine that with precise binaural timing and amplitude differences, and they can localize a rustle under leaves or snow to within a few centimeters. Owls hunting under a snow-covered field can strike a mouse they never saw. Researchers played white noise and small rustles, and the owl used minimizing differences, milliseconds, to lock onto the prey. That's acoustic triangulation. If you could give an owl a human tech upgrade, what would you add? Thermal vision? Microphones? Drop your wildest idea in the comments. Owls combine their silent surfaces with flight kinematics that minimize noise generation. Instead of flapping hard and fast, many species use slow, powerful downstrokes and long, broad wings to glide. Longer chord length at low speed reduces Reynolds number-driven turbulence. When diving for prey, an owl aligns its body and wings such that the talons follow the acoustic vector. It's not aiming visually, but acoustically. The descent angle minimizes pressure spikes and keeps sound below detection thresholds. Metabolically, this strategy is efficient. Gliding requires less power, meaning owls can hover in surveillance mode for long periods, waiting for the acoustic signature of a prey shift. They conserve energy and maintain stealth, a huge evolutionary advantage in winter when calories are scarce. Would you rather be a stealthy, energy-efficient hunter like an owl or a fast, noisy hunter like a hawk? Vote in the comments, owl or hawk. Engineers have been paying attention. Silent wind turbine blades now borrow leading-edge serration geometry to cut aerodynamic noise, reducing neighborhood complaints and wildlife disturbance. That's real-world acoustic camouflage at scale. Delivery drones in 2026 incorporate fuzzy leading edges and trailing edge arrays inspired by owl feathers. The result? Quieter urban flights and less noise pollution. Some companies even use passive sound collecting noses and binaural microphone arrays to locate sound sources, essentially giving drones an owl-like auditory map. Biomimetic sonar. Robotics groups are imitating facial disc-like hoods to passively collect sound, then feeding it into AI that performs acoustic triangulation, the same logic owls use to locate prey under snow or leaves. That tech could help search and rescue robots listen for trapped survivors. Which application excites you most? Quieter drones, stealthy rescue robots, or silent turbines? Tell me why. Owls are brilliant, but their silence has limits. At very high speeds, turbulence still produces detectable noise. And not all owl species show equal degrees of acoustic camouflage. Barn owls are legendary, but other owls trade stealth for speed or maneuverability. There are still mysteries. Exactly how microstructures scale across sizes, how feather wear affects stealth, and how prey species are evolving counter-strategies, like lower frequency footfalls or stiffer leaf litter that broadcasts less sound. What would you study if you had a month in the field with a band of owls? Answer below. I read every comment. If you enjoyed that breakdown, smash the like button. It helps others find these stories. Subscribe and ring the bell so you don't miss future deep dives. New videos come out every Sunday at 7 a.m. Final comment question for you. Do you think we should use owl-inspired stealth in military tech, or keep it civilian only for noise reduction and rescue? Vote and explain your moral stance below. I'll feature the most thoughtful replies in next week's community post. Thanks for watching, and I'll see you in the comments.